this video, we introduce and discuss the basic concepts surrounding regression analysis. We're going to focus initially on bivariate regression, and then in another video show you some examples and how to decompose the variance, very similar to analysis of variance, and then provide different examples. You've probably been exposed to the formula y equals mx plus b. It's taught in most schools, and it's an example of a mathematical function for a straight line. In statistics, we often label this as y equals a plus bx. The a and the b have different functions in this analysis, and the y and x are our variables. The a is called the intercept and b the slope. The intercept, as you know, is the point where the regression function or regression line crosses the y-axis. That is, when the value of x is equal to 0, y equals a. The slope is interpreted as the change in the y-axis for a 1-unit change in the value of x. Of course, we can have other kinds of changes in the value of x, but typically we evaluate it with a 1-unit change. Y is considered our dependent variable, and x our independent variable. I'm going to show you later some different notation that I prefer to this y equals a plus bx, and that I'll use for the remainder of this video in the class. Here's an example we looked at in correlation. When we looked at the correlation between math scores and verbal scores, we saw that they were correlated 0.63, implying that people with high math scores tended to have high verbal scores, that people with average math scores tended to have average verbal scores, and people with low math scores tended to have low verbal scores. I've run the regression and calculated the coefficients, the a and the b. A, in this case, the intercept is 19.9, and b is 0.5. And I've then drawn in the line in the chart, in the graphic at the bottom, and it shows us the general direction and relationship between these two measures. When we see the line go from the lower left to the upper right, the implication is that this is a positive correlation or a positive association. And now we can begin to add a metric to interpreting it. The correlation coefficient 0.63 is pretty good to interpret. We know that this was a moderately strong or strong relationship, but now we can say that on average, every time we see an increase in a math score of 1 unit on that math score scale, we see an associated average increase in the verbal score of approximately 0.5 on the verbal score scale. We can also use this model to make predictions. For example, if I take a value of x equals 50 and I plug it into my model at the top, so I get 19.9 plus 0.5 times 50, then I get a predicted value of 44.9. That is, my model tells me that for people who scored 50 on the math test, my expected value or my predicted value of the dependent variable, the verbal score, is 44.9. You can see that we actually have one case that has a value of x equals 50, a math score of 50, and that person didn't have a score of 44.9. Their score was much closer to 60. And so my model has some error involved in this. Any point on that line is a predicted value. We're going to see that I'm going to label those later as y-hats. Y-hats are predicted values. But in this case, my predicted value, 44.9, underestimates the actual observed value of 60, and that difference is my error. Our statistical models have error in them, and yet we're trying to reduce this by having good theory, well-developed statistics and measurements, and minimizing our error. Throughout this course, we've often looked at the example of sexual frequency. In this case, I'm going to look at the relationship between sexual frequency and age. I've used Stata to produce the graphics and the regression output here. And I've got some Stata code on the left-hand side that shows you how I recoded the sexual frequency variable to convert it to a measurement of number of times per year. When I do regression, I like to look at graphics of the relationship. One of the problems with using data like the GSS, where our sexual frequency variable is not truly a continuous variable, but is actually categorical, even though it's ordered, is that we get this sort of banding effect in the graphic on the left. So what I can do to make the relationship a little more evident is to jitter the points. In essence, what I do is I take each xy coordinate and introduce a little bit of error to it, sometimes adding a little bit in x and y, sometimes subtracting a little bit, and sometimes adding one and subtracting to the other, to kind of push those points around a little bit so they're spread out. And that's the graphic on the right. That graphic still obscures the underlying relationship shown by the line. So I've gone one step further, and for every age, I've calculated the average sexual frequency and then plotted those averages. This means I'm plotting far fewer points, although I'm summarizing the data. And we know that when we calculate averages, even though it's often revealing by getting this sort of summary statistic, we often lose something by giving up the original data. Having said that, this particular graphic I think shows nicely the relationship between age and sexual frequency. We can see that this is a negative relationship, and that on average, as people get older, they report having a declining sexual frequency per year. The data in the upper, or the table in the upper left, is my regression output. This is a very typical looking table. This table happened to be generated by Stata, and I'm going to go through it in more detail in the next slide. But if you notice down on the lower part of that graphic, of that table, I have my age coefficient and something called underscore CONS. Well, that's just how Stata refers to the constant or to the intercept. But those two values, the minus 1.38 and the 118.95, are my slope coefficient, my regression coefficient, and my intercept. That is my beta hat sub 0 and my beta hat sub 1, or my A and my B. And I can take those values and plug them into my model, which I'm showing over on the right, and then I could also use that to make predictions about average sexual frequency. We can see here that for every year that a person ages, there's an average decrease in sexual frequency of 1.39 times per year. That's my slope coefficient. It's negative, so I get direction, and I get a magnitude, in this case measured in sexual frequency per year. Let's go ahead and look at that table in more detail. Most regression output has three different sections to it. In the upper left section, we have our ANOVA table. This is the exact same analysis of variance table that we saw when we did one-way ANOVA. We have our sums of squares, our degrees of freedom, and our mean squares. As in ANOVA, this table in itself is not particularly interesting, but the numbers in this table are used to calculate some summary statistics for our overall linear model shown on the right hand of that table. So moving over to the right, you see that we have an F statistic. The F statistic here with 1 and 1,748 degrees of freedom is 261.69. And as you remember, that 261.69, our F statistic, our F ratio, is equal to the model sum of the mean group between sums of squares divided by the mean group within sums of squares. In the regression context, we call the between group sum of squares the model sum of squares, and the within group sum of squares the residual sum of squares. But they're the exact same thing. We also get the probability of greater than F, that is, we get a p-value. In this case, you can see that the p-value is quite small, 0.0000, so we would find this relationship between age and sexual frequency to be statistically significant. Below that, we see our R squared. The R squared is the ratio of the model sum of squares to the total sum of squares. And in ANOVA, we call that eta. That is, this is the proportion of the total variation explained by or predicted by our independent variable, which in this case is age. That is, 13% of the error in predicting sexual frequency is correlated with or associated with age. And for statistical purposes within sociology, I consider that to be a very large amount. In other words, what we're really saying here is that if I were to make a prediction of the average sexual frequency for everybody in my data set, I would have the total sums of squares as my error. On the other hand, if I used my model and I plugged every age into my model at the bottom of the screen, I would reduce my error by 13%. This table usually is pretty important to look quickly at the p-value and look at the R squared. The table at the bottom, the part of the table at the bottom, is really what's important. On the first line of that table, we get our age coefficients and our information about our independent variable age. We can see the coefficient here is minus 1.386075. And what this says is that for every 1 unit change in age, that is a 1-year change in age, there is a decrease in sexual frequency of minus 1.39. We get a standard error, and this should alert you to the fact that there's going to be a test statistic for the significance of this coefficient. If there's no relationship between age and sexual frequency, the coefficient for age should be equal to 0. If we take the ratio of the coefficient to the standard error, that is minus 1.39 divided by 0.086, we get a t-statistic, in this case minus 16.2, which tells us that this particular variable is statistically significantly different from 0. That is, the coefficient is different from 0. We also get a p-value, so if we don't want to use the t-table in the back of the book, we can go right to the p-value. Finally, we get a 95% confidence interval around our coefficient 1.39. That is to say, the coefficient here, 1.39, is an estimate. And like all of our estimates, it has a certain margin of error, and we can capture that in a confidence interval. In this case, a 95% confidence interval. The next row of this table gives us the analogous information for our intercept. Our intercept here is 118.95. I'll call it 119. The interpretation of this particular intercept is really not meaningful. What it says is, when the value of x is equal to 0, the value of y is equal to 119. That is, when somebody has 0 age, which is impossible, we would predict their sexual frequency of 119 times per year, which is obviously pretty silly. When we try to extrapolate beyond the range of our data, looking at people that are extremely old, there's nothing to prevent us from plugging in a value of 150 as age or negative 150 as age. We can get nonsensical values. An age of 0 really doesn't make sense here, and so we shouldn't spend a lot of time interpreting this particular statistic. But note that it too has a standard error. The null hypothesis is that the intercept is equal to 0, and we could reject that hypothesis with a very large t-statistic of 27.72 and a very small p-value. Let's look at my preferred notation. Here I've got 4 different models. The first 2 at the top describe populations, and we can tell that because we're using Greek uppercase letters, and there's no hats over those Greek letters. So y equals beta hat sub 0 plus beta hat sub 1x plus e is a population model. Remember that we typically don't have access to the populations, and so this is something we'd like to make an inference about even though we don't know it directly. Just below it, I'm showing y hat equals beta hat sub 0 plus beta hat sub 1x. Again, this is a population model, and this represents the actual regression line. That is, those y hats are the predicted values from our model and lie perfectly on our regression line. The bottom 2 formulas describe samples. And I know that these are from samples because my Greek letters have hats over them. So y equals beta hat sub 0 plus beta hat sub 1x plus e is a sample-based model, something I would actually calculate using my regression model, my regression statistics, and maybe present in a table or paper, and use that to make inferences about the population model. And I can express this both with error and without error by using y hat. Again, this implies that every point is generated by my model and lies on my regression line. To get a handle on regression, you have to understand the slope. So we know that the slope is beta hat sub 1 or beta sub 1. You may have heard this in another class as delta y over delta x. That is, it's the change in y divided by the change in x. In this example, we have some point y sub 2 minus y sub 1, change in y, divided by x2 minus x1, that is the change in x. At this little example down below, based on the data, we get a slope value of 2. And you can see that every point lies on the line. There's no error. And solving for our regression here, we get a regression function equal to y equals 5 plus 2x. When we have a linear function, a linear regression, we can see kind of a stair-step function. That is, every time we increase x by 1, in this example going from, say, 2 to 3, we see an associated increase in y of 2. That is going from 9 to 11. And this function holds whether we're looking at the change in x from 0 to 1, or 1 to 2, or 2 to 3, or 3 to 4, or 4 to 5. Anytime we see a 1 unit change in x, we'll see a 2 unit change in y. And that's partially what defines a linear function. If we saw that the steps were changing their slopes, sometimes it was a 1 unit change in x and a 2 unit change in y. Another time it was a 1 unit change in x and a 3 unit change in y. We would have a nonlinear relationship. The other thing to notice here is that we have no error, which is unrealistic in actual sample data, and particularly in the social sciences. What we're really describing above is a mathematical function, and again, you have some experience with mathematical functions. For example, you know that to convert from centigrade to Fahrenheit, you can use the formula that Fahrenheit is equal to 32 plus 9/5 times the centigrade temperature. And that fits our general model of y equals beta hat sub 0 plus beta hat sub 1x. The difference between this particular mathematical function and a statistical function is that there is no error. If you tell me the temperature in centigrade, I can perfectly tell you the temperature in Fahrenheit. In our social sciences, as we've discussed before, we have a lot of inexactitude in our measurements. We have measurement error, we have sampling error, and of course people don't always do the same things consistently. There's free will. And we encompass that into our model with adding an extra term at the end of our model, which is our error term. So in the social sciences dealing with sample data, our regression model is typically y equals beta hat sub 0 plus beta hat sub 1x plus e for error. And we'd like to minimize the error by producing good models and good measurements, but we're not always so lucky or able to do that. Here's a regression model that also shows that y equals 5 plus 2x model, but you can see that at each value of x, not every point lies exactly on the regression line, that there's a range of values for each value of x. There is a range of responses of y that fall around that regression line. It's that range of values around the regression line that is our error term. And we can measure error very directly in any model as the location of each case minus the predicted value, that is y minus y hat. And so we can get a sense of how good our model is by seeing how close all the points lie to our regression line. Well, how do we come up with this line? One way to do this is we can just start putting lines through points in space and seeing which ones fit best. People have referred to this jokingly as an interocular stress test. Draw a line graphically through your points, pick the line that appears to fit the data the best, and that it's the one that hits you square between the eyes, the interocular stress test. But we also would like to approach this mathematically to have a more precise answer. I'm going to show you one method of looking at this, and it turns out that it's not going to be that helpful, but it provides the foundation for understanding the actual way we calculate this statistic. Here we have x and y, and I only have 3 points. And I'm giving 3 different lines through those points. You can see that in some of the graphics, the lines look pretty good. That is, I would say that this is a positive relationship between x and y. And in some of the graphics, the relationships look pretty bad, showing a negative relationship. How can we calculate, or how could we understand mathematically, the distance of all these points from the line and then pick a line that minimizes that distance? Well, we know that we can measure error as the distance of each point to the line. And we're going to go ahead and do that for these 3 graphics and calculate what's called the total prediction error. The total prediction error is actually not going to be helpful to us, but it does make a point. If I calculate the total prediction error here, we can see that line 3 is the best fitting line because the sum of the error from that line is equal to 0. But it also points out the problem with this. If we think of our regression line as an average or representing averages, and we take deviations around an average, we can come up with the value of 0 and really not understand the relationship. So like we've done in other parts of our statistics class, we're going to calculate this statistic a little bit differently. If somebody asks you what the mathematical goal of regression is, one answer is that it's to minimize the SSE, or the sum of the squares of the errors. That is, we're going to go ahead and calculate the error as y minus y hat, but we're going to square that difference. It's the squared differences that we're attempting to minimize. And there's a very straightforward formula derived from calculus, shown here, that we can calculate the best fitting regression line. Now, when you look at the formula for the slope, beta hat sub 1, you'll see in the numerator something we saw in correlation. We have the sum of the cross products, or the covariance of x and y. And all we're going to do is divide that covariance by the variance of x. You remember from correlation, the covariance did a couple of important things for us. It gave us the direction of the relationship, whether the correlation coefficient would be positive or negative. And it does the same thing here. It's going to give us a direction to our regression coefficient, beta hat sub 1, and it will be positive or negative. It's also going to give us the magnitude of the coefficient. That is, we're going to get values that are small when there's very little relationship between x and y, and values that are large when there's a substantial relationship between them. We're dividing by the variance of x to scale this variable so it's no longer a correlation coefficient between minus 1 and 1, but we're going to be able to interpret this coefficient as a change in y, whatever our dependent variable is, on average for every change in x. Once we have beta hat sub 1 in hand, we can go ahead and calculate the intercept, or beta hat sub 0, which is simply the mean of y minus beta hat sub 1 times x bar. There's other formulas that we can use. The one that's most useful for doing things on exams and so forth is the formula for the slope in the upper left. It also shows us an interesting principle of the slope. If we take the correlation coefficient, Pearson's correlation coefficient of y and x, and multiply it by the ratio of the standard deviation of y to the standard deviation of x, we get our slope coefficient. And it's this kind of interesting situation that says, if I think about this, when could I have two different variables that have exactly the same standard deviation? Well, if I converted both of my variables to z-scores, they'd both have a standard deviation of 1. And this tells me then that if I calculated beta hat sub 1 for the z-score of y regressed on the z-score of x, my beta hat sub 1 coefficient would be equal to the correlation coefficient between these two variables. So mathematically, correlation coefficients and regression coefficients are really intimately related to each other, the only difference being a scaling factor, where the correlation coefficient is scaled to be between minus 1 and 1, and the regression coefficient is allowed to be measured in the units of y. There's also a computational formula, which, again, like our other computational formulas, I hope you don't have to use. Well, you might do one or two of these by hand to practice, but when all is said and done, you're going to end up using a statistical package like SAS or Stata or SPSS to calculate these things, and hopefully never have to use a handheld calculator again. Not only will you get more precise results with less error, but you'll have the ability to have programs that can be repeated and replicated and produce the same answer every time you run them. That's the end of this particular video introducing you to bivariate regression. As usual, if you have any questions, please let us know and we'll try to answer all of them. See you in class.